So yeah, I just wanted to, I was just curious as to what got you interested in cybersecurity or crypto, and also sort of your understanding of what crypto is, right? So today we will mostly talk about modern cryptography. But before we get started even talking about modern cryptography, for instance, cryptography comes into play wherever digital information comes into play. And right now, digital information is everywhere. There's, computer systems everywhere, right? But if you think of, say, few centuries ago, cryptography was described as sort of the art of solving or coming up with codes, right? So crypto was really thought of as these classical ciphers that one might take into account, and we are like far away from that notion today, right? So just to sort of motivate, the setting and sort of the foundation and definitions of modern cryptography, I thought we'll just start with some example of ciphers. I think you might have seen a couple of them, or I mean quite a lot of them yesterday. But just sort of to get going about historical ciphers. So is my handwriting legible and big enough? So please ask me to write bigger if you need me to, okay? So has anyone come across the shift cipher? So did you discuss that yesterday? Yeah, okay, cool. Yeah, so excellent. So when you were thinking of, say, attacking the shift cipher, right? So for instance, so, like shift cipher has some key k, right? I don't know if this is the terminology used, but one can think of the key k as a single letter of the alphabet, and if we map each letter of the alphabet to its counterpart in terms of numbers, so if we map A to 0, B to 1, etc. up to Z to 25, we can think of the key k as one belonging to the set 0 through 25 of the shift cipher, right? So essentially, if there is a word, say crypto, right? So this is the plain text, and the key k, say, is B, right? Essentially, we will just shift each letter of the alphabet that corresponds to the plain text by B, right? So B here implies 1. So essentially, C will become D, R will become S, Y will become Z, P will become Q, T will become U, O will become P, right? So this is essentially what the ciphertext would be, right? So, so at least I hope I have reminded everybody of the definition of shift cipher that you saw yesterday. Any questions on just the definition here? Okay, so now, I mean, I can ask you this question, right? I can ask, is shift cipher secure? Okay, so this is the question I am asking you. So before, I just want to sort of establish this before you answer. If you want to answer or if you want to ask a question, just so that it makes it easy, raise your hand and I will call you and then you can answer the question, right? So is shift cipher secure? Any answers? Yeah?
It's not secure.
It is not secure. Okay, any other answers?
It's B to brute force. You can literally brute force all combinations in a matter of minutes.
That's right. So essentially, right, so the answer that we have is no, right? And sort of his reason is that you can easily perform a brute force attack. Okay, so what do we mean by this? Again, maybe was brute force attack introduced to you yesterday?
Yes.
Yeah, okay, right? So essentially, I mean, I'm not going to spend much time on it, but essentially the idea is that the key is one of these 26, numbers or letters. So essentially, you take the plain text, you try each of these keys, you take the ciphertext, right? You try each of these keys, you figure out what the plain text is and see if that plain text is something that makes sense. Okay, so if it's something that makes sense, then you think that, okay, this must be the plain text. So it's very easy to brute force because, I mean, trying out 26, we can even do it by hand. We may not even need a computer, right? So apart from this, there is also actually another attack to sort of figure out the insecurity of shift cipher. Does anyone know what that is or has come across that? Sorry? Frequency analysis, that's right. So yeah, you can either perform say a brute force attack or you can perform a frequency analysis. So was that also mentioned yesterday? Yeah, okay, cool. So I will not spend much time on it to remind you guys of what that is. But essentially, right, you can observe the cipher text and see which letter of the alphabet sort of occurs with most frequency, and then you guess that, so say if S occurs with most frequency in the cipher text, this must be essentially what the most frequent letter that occurs in the English alphabet is mapped to as, so that would be E. So then you sort of figure out that the key K is S minus E, right? So this is sort of how you would do, I mean very a preliminary idea of how you would do frequency analysis. Okay, but so this is good. We all have an understanding of what the shift cipher is, right? And then we could somewhat discuss, maybe meaningfully discuss the security of the shift cipher and also how to attack the shift cipher, right? But let me sort of mention something else. So yesterday did you also come across the Visionaire cipher? Yeah, Visionaire. Okay, cool. Yeah. Right. So in Visionaire cipher, right, so again we can think of the same plain text as crypto, right? And now if you recall the key, right, instead of being a single letter of the alphabet as it was here would be a phrase, right? And essentially the phrase would be repeated multiple times as required to sort of cover the entire length of the plain text. So for example, we can think of the key as the phrase say dog. Okay, essentially then to encrypt crypto, right, we will just repeat dog as many times as we require and essentially just perform shift as we did before, right? So C will now be shifted D places, R will be shifted O places, Y, G places and so on and so forth. So this is the Visionaire cipher. So I hope the definition is clear to everybody and you're reminded of it. So is the Visionaire cipher secure? So you can take a couple of minutes to think about it. Yeah.
Again, the answer is no. And brute force is obvious. You can also refer to a dictionary of keys. If you know somebody's taking, a word as a key instead of this random string, then you can brute force with the dictionary as well.
So the brute force attack may not be as efficient here as it is in the case of the shift cipher, because for instance here we know the length of the key is 1, whereas here the length of the key, right now it's just dog, but it could be something that's much larger. But actually rather than the brute force attack, you can use, if you knew the length of the key, say, you could perform frequency analysis, right? So essentially if the length of the key, so that is called the period, so here the length of the key, the period is 3. If you knew the length of the key, then essentially, right, you know that after every 3 occurrences, sort of the key repeats and it essentially becomes the shift cipher. So you can look at, maybe it's cryptography, right? So you can just look at C, P, G, P, right, assuming that you know the period of the key, and then again perform frequency analysis to check, okay, so C, C shifted by D would be D, E, F, G, right? So essentially again analyze each of the letters of the ciphertext, perform frequency analysis to figure out what it should actually map to. So what would be the first character of the key, and similarly for each shift of the key, right? So you could perform this frequency analysis for each shift of the key. So is this idea okay? Okay, so in this particular example, maybe it works out, okay? But what if, is there a setting where the visionary cipher could be secure? Sorry? Larger text and larger text implying plain text. But what about the key? So actually, I saw multiple hands. I'll come to each of you, but yeah, I prefer that everybody. So key should be small or large then? So yeah, I'll come to you. Yeah. So then for visionary cipher to be secure, should the key be smaller? Larger. Okay. Somebody else had one time pad. Okay. Yeah. So was one time pad covered yesterday? I see. Okay. Right. So were there other answers? But yeah, that's essentially right. So essentially, in the case of the visionary cipher, if the length of the plain text is exactly the length of the key, right, as would be the case in the one-time pad, then the visionary cipher is essentially a one-time pad, and in that case, it would be secure. Okay. So since this was covered yesterday, I will not spend much time on it. But really, what I wanted to bring out in this discussion is when we are sort of engaging in this question and answer session right now, I just asked, is this cipher secure? And somehow by my question, you had some understanding of what security meant, although it was not formally defined. So what does, to you, what is security? Right? So when you were saying, when you were answering that shift cipher is secure or not secure, so it's not secure. And when you were answering that visionary cipher is secure in some cases and not secure in some other cases, what actually were you, what sort of, what was your brain mapping secure to? Time taken to crack it. Okay. Other answers? Yeah.
Something that meets the criteria of a transaction or a message that meets the criteria of being confidential, having its integrity, and authenticate.
So when you say all of these words, what do you mean?
These are like the metrics. Anything that matches the metric, these metrics is considered secure.
So that is fair, but what I'm saying is, so you've now changed the word secure to say confidential, right? But what does now confidential mean to you?
The confidential basically means secrecy, as in only the people who are supposed to know the information, and it does not leak anywhere else.
Sure. So I mean, I think this is sort of contributing to the discussion where we have these ideas, and maybe to me, what is confidential could mean that only I know the answer and nobody else. But say for you, what could be confidential is only you and your friends from college know the answer, know the message, and nobody else. So we have to establish exactly what confidential, or to my point, what secure means. So there were other answers? Yeah.
So like how much effort is required?
How much effort? So similar to the time taken, right? So other thoughts? Yeah. Provided we know the algorithm, whether it's feasible to break, right? But what is feasibility is the other question, right? Yeah. Should resist the attacks with current computational power. Yeah. Other thoughts?
Like larger the cost to break something, then lesser the chances of being that.
Okay. So similar to, yeah, computational cost, right? Yeah. Other thoughts? Right. All good answers, but also this reflects that each of us has some idea as what security means, but really sort of the goal and like the last 3 decades, what modern cryptography has done is exactly formalize precisely mathematically what it means to be secure and under what assumptions it can be secure, and then sort of show a proof of security that these things are secure, right? So that's what essentially we will see in the rest of the day. about what, when I say the secure here, right, and we can even analyze each of these schemes under this meaning of security, right. So for instance, for somebody, a scheme can be secure if the key is never revealed, right. But to your point, maybe the key never gets revealed, but the message is completely revealed in the clear. So is that secure, right? For someone else, it could be that, maybe a large portion of sort of the data is not revealed. But then maybe, again, what is a large portion? And maybe say it's some salaries of everybody who's working here. And there it might matter even if one salary gets revealed, right? So we have to precisely quantify what we mean when we say secure. And really sort of the notion that is now accepted is that from the observation of the ciphertext, okay, so for instance here, right, this was the ciphertext. From the observation of the ciphertext, an attacker's knowledge of the underlying plain text should not be more than what it was before. Okay, so if without observing the ciphertext I had no idea that the plain text was crypto, even after observing the ciphertext I should have no idea that the plain text was crypto. Okay, so that is sort of one informal way as to how we would formalize what security means in this context. Again, just to sort of backtrack, we are talking about, when we are talking about these codes, we are talking really about encryption schemes, so I'll spend some more time on it in a bit. The other thing, again, I think some of you raised this point, is that, so I said, okay, somebody who observes the ciphertext should not be able to have any more information about the underlying plain text before they had observed the ciphertext. But who is this somebody, right? And what computational resources does this somebody have? Do they just have a laptop computer? Do they have sort of like, 50 computer strong network? Do they have a supercomputer, like the world's fastest supercomputer? So what are their resources? So who are the adversaries that we are trying to protect the ciphertext from? Is this just people in this class, or is this, say, NSA, right? So these are also the other things that we need to formalize. So apart from formalizing what precisely security means, we need to formalize against which sort of attackers we want to establish the security. Okay, so this is what we will see. So essentially we will see various security notions today. Okay, so any questions on the discussion or just the motivation of what we will see today? Okay, so then before we get started, let me just talk about what is the setting of all of these ciphers in some sense, and private key encryption. So in all of these codes that we talked about, right, even though we didn't explicitly mention it, implicitly we were assuming that there was a sender, right, and a receiver, and each shared a key K between them. Right, so for instance, in the case of the Visionaire cipher, this key might have been the phrase dog, right. So the sender and the receiver shared a key K between them, and the sender, who's holding some message M, wishes to transfer this message M like securely to the receiver, right, and they will transfer this using a ciphertext C, where the ciphertext C is the encryption of the message M under the key K. Okay, so this is what we were talking about, even though we did not explicitly mention that, right. So this setting is okay. So this essentially is the setting of private key encryption, okay, and more formally, even before we talk about what security notions we are considering, what sort of attackers we are considering, in sort of, like the foundation of cryptography and theoretical cryptography, we talk about the syntax of the scheme, right. So now we have the sender and the receiver who have shared a key K. So how is this key K generated, right? So essentially, then an encryption scheme will come with a key generation algorithm. Then this encryption scheme will specify an encryption algorithm that on input a message M and key K produces a ciphertext. Okay, and then this, so essentially the sender has this message M, right? The receiver, upon receiving the ciphertext C, should be able to decrypt that ciphertext C under the key K to output the message, say M prime. And correctness would require that m and m prime are identical. So essentially whatever the sender wish to encrypt or sender wish to send across to the receiver by encrypting the message m should exactly be the same m that's recovered by the receiver when the ciphertext that was received is decrypted using the decryption algorithm with the same key k. Okay, so this is sort of the syntax of an encryption scheme, and I will form, so since again like I said, formal definitions are important, I will formalize this and then you can ask me if there are any questions. Right, so formally, a private key encryption scheme is defined by specifying a message space, calligraphic M. So, a message space, for instance, here is sort of the set of alphabets in set of letters in the English alphabet, right? So, essentially repeated as many times as it wants. Okay, so this is the message space in the case of the Visionaire cipher. So, for instance, in the one-time pad, you can just think of it as 0, 1 to the L, where L was the length of the bit string. Okay, so you specify a message space M along with 3 algorithms. So these algorithms are a procedure for generating keys, so which will be called the key generation algorithm gen. Okay, a procedure for encrypting, which we will refer to as the encryption algorithm enc, and a procedure for decrypting, which we will refer to as a decryption algorithm dec. Okay, so then the algorithms will have the following functionality, right? So the key generation algorithm gen is a probabilistic algorithm So probabilistic implying it takes in some randomness. So every time you run gen, it may not output the same output, right? So the key generation algorithm gen is a probabilistic algorithm that outputs a key k according to some distribution. So for instance, in the case of the shift cipher, you can imagine it outputs A through Z with uniform probability, right? So A is chosen with probability 1/26, B with probability 1/26, and so on and so forth. And every time you run the key generation algorithm, it may not be the same key that is generated, right? So one time it could be A, another time it could be B. So that's the key generation algorithm. The encryption algorithm enc takes as input a key k and a message m and outputs a ciphertext C. Okay, so part of defining all of this is also to define notation. Okay, so when the encryption algorithm is run in the following manner, we denote this as C output by running enc on the message m under the key k. So the key k is a subscript. Okay, so this is sort of the notation that we will use. So then finally, the decryption algorithm DEC takes as input a ciphertext C and a key K and outputs a plain text M and we will refer to this as M output being output by the decryption of the ciphertext C under the key K. Okay, so this is just formalizing sort of the informal discussion and the picture that we had. So I'll just leave this up here for a minute. Ask me if there are any questions. So also just for reference, most of what I would be talking about today is from the textbook Introduction to Modern Cryptography by Katz and Lindell. So once you go back, you can refer to it, to the sections that I covered today, or maybe just go ahead and read it, and if you have any questions also, you can email me later. The name of the book is Introduction to Modern Cryptography by Katz and Lindell. So any questions on the syntax? Right, so just to sort of recap what we saw, you can picture that this is exactly what's happening when we run a private key encryption scheme. Right, so there is this sender and the receiver that we talked about. Okay, so there will be a key generation algorithm. Okay, I guess to be a bit more formal, so if they are running some private key encryption scheme pi, right, so pi will consist of three algorithms: the key generation algorithm gen, the encryption algorithm enc, and decryption algorithm dec. So in order to specify any private key encryption scheme, you need to specify these three algorithms, right? So I'm considering the scheme pi that consists of these algorithms gen, enc, and dec. Okay, and now how would a sender and a receiver use this encryption scheme pi? First, the key generation algorithm gen would be run to obtain some key k. Okay, so this is the key k that is shared between the sender and the receiver. Okay, and now if the sender wishes to send a message M, the sender will use the encryption algorithm, which takes the plain text M and a key K, computes the ciphertext corresponding to M under the key K, and sends C to the receiver. Okay? And then the receiver, again knowing that they are using the private key encryption scheme pi, when it obtains a ciphertext C, will now run the decryption algorithm of pi on the ciphertext C under key K to obtain some message. Okay, so this is how pi with the algorithms gen, enc, and dec will get used. Make sense? So in order to complete this definition of a private key encryption scheme, what is one condition that is missing? M equal to M prime, that's exactly right. Right, so essentially what we want is not just this decryption algorithm under the ciphertext C and key K outputs some M prime. We want this to be exactly the M that was encrypted. So essentially, right, so this is what we want, and this is called the correctness condition. Right, so what we will want, so apart from stating this as the syntax, the private key encryption scheme should also satisfy a notion of correctness. Again, note at this point we are not yet talking about security, we are only talking about correctness, right? So, for every key k output by the key generation algorithm gen and every message m belonging to the message space calligraphic m, it holds that the decryption under key k of the encryption under key k of the message m is equal to m. Okay, so this is the correctness condition. So for instance, let me ask you the following question to make sure the correctness condition makes sense. So we discussed the shift cipher. Does the shift cipher satisfy the correctness condition? Yes, right? So please raise your hands and answer. But yeah, so the shift cipher satisfies the correctness condition. So correctness has nothing to do with security. It is just the functionality that we expect from the scheme, right? So this is just the basic syntax that we established so that we can now formally talk about encryption schemes. So is the syntax clear? Is that making sense? So I'll just leave it up for a minute. If there is any question, you can ask me. So if there are questions, if you discuss with the entire class, it would benefit all of us. So did you have a question? Just trying to understand, that's fine. Did you have a question? Yeah.
We are talking about encryption while the key is being shared, so we can.
How do we share the key? Oh, excellent question. So for the first half of today, I will not talk to you about how the key is shared, okay? But so just to, just so that it, I guess eases your mind, you can assume that maybe, like you and your friend, meet today, share a key k and then go your separate ways. And then you are, encrypting. But maybe you are also thinking about this because you have come across public key cryptography. Is that possible or not because of it? Okay. But yeah, it's a very good question. So yes, the key generation algorithm is only providing the key k and somehow the key k is shared in advance, right? So the assumption throughout sort of the next couple of hours would be k is shared in advance between the sender and the receiver, so between the two parties. Right, and also that k is kept completely secret. Okay, so how the k is shared in advance, like I said, maybe two people know that they are sort of, they will be having some important communication, so they just decide to share a key and then they can use it later. Or for instance, right, so another context in which these things get applied is, for instance, you might want to encrypt your hard disk. Okay, so really here the sender and the receiver is both you. So you have the key k, you have encrypted your hard disk, and at a later point you can decrypt the hard disk and read its contents. So yeah, but this is a very good question. I will not talk about it now. I will talk about it in 2 to 3 hours. Okay. Other questions? Okay. So like I said, please feel free to stop and ask me questions at any point. If there is some doubt that comes up later, do ask me. Okay, so I'm assuming that the syntax is clear. So just so that we have, we can just play around with it a bit more, and also because I will talk about the security definition that relates to the one-time pad. Maybe what I will do before I even write it down is, okay, so you have the syntax now. You saw the one-time pad yesterday. So I'm not sure exactly what the notation that you used was, but maybe just to get that going, let us consider now the one-time pad, okay, and let the message space be essentially L-bit strings. Okay, so then any message m that you encrypt will be an L-bit string, right? The key k would also be an L-bit string, and you will perform encryption by XORing m with the key k. right? So I hope this is what you saw yesterday. Sort of with this idea that you have, can you write down what the key generation, encryption and decryption algorithm would be for the one-time pad? So you already have the idea of these algorithms. I just want you to write this in this sort of in this language that we have discussed. So take a pen and paper and try to write down. Sorry? Water, oh yes, water please, yeah, thanks. Thank you. So what is the key generation algorithm for the one-time pad? So how would you define gen? Yeah. Toss a coin for L times. So essentially if the coin comes up heads, you then think the first bit of the key is 0 and essentially for L times you, okay. So, but how would you formally write it down? Right, so you consider the uniform distribution. So, right, so consider the key space. So I didn't define what key space is. Again, I'm not going to be defining it as much as I would define if I had, say, a semester long lecture. So I'm assuming some things are making sense. Okay, so the key space is a set of all possible keys. So since the key is of length L, the key space, so calligraphy K is 0, 1 to the L. So choose a key K from the key space according to the uniform distribution. So when I say uniform distribution, what I mean is that all the, so how many keys are in the key space? 2 power L, right? So there are 2 to the L possible keys. So you choose each of those 2 to the L possible keys with probability 1 over 2 to the L, right? So you'll just choose a key K according to the uniform distribution. So a key K in 0, 1 to the L. So each of the key K, I guess, each of the keys K in 0, 1 to the L is chosen with probability 2 to the minus L, right? So essentially we are following the uniform distribution. So this is key generation, right? So you are choosing a key K uniformly. Okay, what is the encryption algorithm for the one-time pad? Yeah, sure, yeah. So but it's fine for us to even consider XOR of bit strings itself. So on input a message M, that's an L bit string, because the message space is set of L bit strings, and a key K, that is an L bit string, output ciphertext C as M XOR K, right? So this is what you would have seen yesterday, but I'm just writing it in the language that we have discussed. So similarly, what is a decryption algorithm?
XOR C and K.
Right.
And the output should be.
So should be M does not come part of the algorithm. Yeah. So essentially, what we would say is on input a ciphertext C and a key K, output message M as M equals C XOR K. Okay, and we can see that this satisfies correctness. Okay, so this is what, so how can we see this, that this satisfies correctness? M equal to M essentially, right? So what do we mean by that? So decryption under key K of encryption of M under key K is decryption of key K under encryption of M under key K, which is defined as M XOR K here, and then decryption is defined as whatever this is, right? So M XOR K XOR k, right? This is the decryption algorithm which gives us M. Okay, so we see that it satisfies correctness. Okay, so this is the one-time pad. I mean, again, at this point, I'm not really teaching you anything new about the one-time pad, but really sort of teaching you the language in which we will discuss schemes. Is this making sense? Okay, so then we are ready to see our first security definition. So, did you see any security definition yesterday with regard to the one-time pad? So, the one-time pad actually satisfies a notion called perfect secrecy. Okay, so let me define what that notion is. So, maybe I'll sort of erase the thing in the middle because this is what I wrote first. So, this is our first formal definition for today. So, what we mean by perfect secrecy is essentially what I was trying to convey earlier with regard to the intuition, right. So, here an adversary that observes the ciphertext, say the ciphertext C here, should not be able to say anything more about the underlying plain text than it could have prior to observing the ciphertext. Okay, so essentially the a posteriori distribution of the message M after the observation of the ciphertext should be identical to its a priori distribution. So, that is really what perfect secrecy formalizes. So, an encryption scheme pi consisting of gen, enc and dec with message space M is perfectly secret if for every probability distribution over M, every message M belonging to the message space and every ciphertext C belonging to the ciphertext space. So, essentially ciphertext space is the space that consists of all ciphertexts that you obtain by running the encryption of the message M under key k, where key is according to the key generation algorithm. Okay, so that is a ciphertext space, although I didn't formally define it before, for which probability C, so the ciphertext obtained C occurs with non-zero probability. So, an encryption scheme is perfectly secret if the probability that the message is indeed M after the observation of the ciphertext C is identical to the probability that the message is just M. Okay, so probability M equals M, condition on C equals C equals probability M equals M. Okay, so essentially what this implies is even after observing the ciphertext C, your understanding of what the underlying message M could be, so the probability with which that message could be M is exactly identical. So, if this holds, we say that the encryption scheme is perfectly secret. Okay, so I'll just leave this definition up for a minute. So, this is just a technical requirement so that you don't condition on something that is 0. So, you can, if just to understand, you can even like ignore this for a bit. Just for your intuition, you can ignore this for a bit. This is just a technical requirement. So, but sort of the underlying intuition is that you observe the ciphertext C and still sort of your understanding of what the probability with which the message could have been M does not change. So, what I would encourage you to sort of do, after the fact or maybe during the break is sort of, try to define, so take an example of say a shift cipher, right? Define your own message space, right? Maybe probability of the letter A being encrypted say is like 0.6, letter B being encrypted is 0.4, so these are the only two. And then say you observed some ciphertext C, you can then try to sort of just figure out what these probabilities would be for that particular example. And actually the textbook has such examples, so I definitely encourage you to sort of after today, we may not have time to do a lot of examples during the class. So those that are somewhat, maybe the next definition I will actually encourage you to, we will do an example in class so that you get familiar with it, but this one I will not, because after sort of this, the next 10-15 minutes, I will not be working with this way of defining this. So we will still be working with perfect secrecy, but I will present another definition that is easier to work with. But I just wanted to introduce this because it's sort of the classical way of viewing things. So any questions on the definition? It might be a bit wonky, but I encourage you to take a look at it later. So there are actually equivalent ways to define perfect secrecy. So in fact, the one-time pad that you saw yesterday and we defined today is actually perfectly secret. So what do I mean by the one-time pad is perfectly secret? It means that this encryption scheme that we defined here satisfies this notion that for every probability distribution over M, every message M, and every ciphertext, where the ciphertext is obtained by this encryption algorithm, this condition holds. So I'm not going to go through the proof, but it's actually a simple and nice proof, so I'll encourage you to take a look at it. But yeah, this is sort of an important thing where, so one-time pad is considered a classical cipher, and why exactly it's classical we'll come to in a bit, which actually has, satisfies an important security definition that we want. Okay, so before we sort of play with the definition a bit more, I want to introduce an equivalent definition, okay, and this is sort of done using a game, and these sort of definitions we will look at repeatedly today. So that is why this is the definition that I would like us to focus on. And so this definition is called perfect adversarial indistinguishability. So this is equivalent to perfect secrecy. So it's equivalent to this definition, okay, but it is sort of defined in a different way, okay. So we will define this using an experiment. So consider the following experiment, so which I will call the adversarial indistinguishability experiment, that I will name priv k EAV A comma pi. So, and I will explain first the terminology before we discuss what the experiment is. Okay, so it's called priv k here because we are in the private key setting. So what I mean by private key setting is when we consider the sender and receiver, they both shared a key k and used. So private key or symmetric key setting is when both the sender and the receiver share a key k, which will be used for say encryption. Okay, so for now that is the setting we are in, and when we talk about public key cryptography, this will no longer be the setting we are in. So in order to distinguish between the two, this is we call this priv k. Okay, we call this EAV, which again relates to some of the points that came up when we were discussing how to define security, right? So when we were discussing how to define security, one thing I mentioned is, okay, like for instance, how do we define confidentiality, right? So here we chose to define confidentiality in the following way. So where I say that even after observing the ciphertext, you have no knowledge about the underlying plaintext, no additional knowledge about the underlying plaintext. But there were other points that we discussed. For instance, we were talking about computational cost of the attackers. And if you see in this definition, it doesn't necessarily talk about a specific attacker or computational cost. So what that really means is that this definition is expected to hold against, in a sense, all possible attackers. So there is no computational bounds actually. So it's really talking about all possible attackers. And then another point that I didn't spend a lot of time on, but really when we talk about attackers, what could they see, right? Like for instance, in this again discussion we were having, we were only talking about observation of a single ciphertext, C. But for instance, right, there could be an attacker who could maybe observe multiple ciphertexts, C1, C2, etc. up to CT, right, and then observe C, and maybe that gives the attacker some power, okay. Or maybe there is an attacker that can request for encryption of M1, right, and then receive encryption of M1 as C1, request for encryption of M2, so essentially, go on for I times, right. So requests, choose its own MIs, choose its own plaintext, request for encryptions of those plaintexts, observe the, obtain the corresponding ciphertext CI, and is then trying to guess what the underlying message of C is. So for instance, for those of you who might have come across it, these are called chosen plaintext attacks, right, where the adversary can choose the plaintext and then observe, obtain corresponding ciphertext, and then it's trying to observe or understand what the underlying plaintext of the C is, okay. But we did not talk about this so far, right. In our discussion, for instance, of the shift cipher or the visionaire cipher or even the one-time pad, we were not in this setting. We were just in the setting where the adversary is seeing some C and is trying to figure out what the underlying M is. So this setting is called the setting of an eavesdropper, where all the adversary is doing is eavesdropping across a channel and is eavesdropping across only a single ciphertext, okay. And we can consider stronger settings, and which is what we will do as the day goes on, okay. So that is why we have the superscript of EAV here. So priv k indicating we are in the private key encryption setting, EAV to indicate that we are in the adversarial setting where the adversary is only eavesdropping a single ciphertext, okay. And A would be sort of the adversary that we will consider specifically to this experiment, and pi indicating the encryption scheme against which, for whom we are considering security, okay. So this is really what the notation is, and as we keep going, by the end of today, I hope you guys will just be able to say this in your sleep, but we will get adjusted to it in a bit, okay. So let me define what the experiment is, and then I will not discuss its equivalence to perfect secrecy, but it is sort of the definition that we will work with, okay. So we will consider the following definition. So here we consider some adversary A, okay. So we haven't discussed what the adversary A is and what its strategy is, but that is sort of what we will do when we will try to attack a scheme. So we are considering an experiment where this adversary A outputs a pair of messages, M0 and M1, that belong to the message space. Then a key K is generated by using gen, which is the key generation algorithm of this pi, right. So when we specify a pi, it comes with its own gen enc and dec, right. So that's the syntax we have agreed to. So this key K is generated by using the key generation algorithm gen, and now a uniform bit B in 0, 1 is chosen. Okay, so once I formalize it, I will informally discuss it, so I hope it becomes clearer then. And the ciphertext C corresponding to the encryption of the message MB, right. So there were two messages M0 and M1. One of these two messages will get encrypted. So that is this message MB. So, and that will be decided by the uniform bit B that is chosen. So the encryption of the message MB under the key K that was obtained using the key generation algorithm is computed and given to the adversary A. Okay, so I'll write here, I hope you guys can sort of switch over there. Okay, and this C that is given to the adversary A is called the challenge ciphertext. Okay, so we refer to C as the challenge ciphertext. Okay, now the adversary A outputs a bit B prime. Okay, and the output of the experiment is 1 if B prime equals B and 0 otherwise. Okay, so if the output of the experiment is 1, we write this as priv k EAV A comma pi equals 1. If output of experiment is 1, and in that case we say A succeeds. Okay, so before I write down the formal definition, let me just discuss what is going on here. So, we are trying to formalize what security means in the setting that we talked about. There is a sender and the receiver, there is an encryption scheme pi, there is, the sender sends a single ciphertext C across the channel, and an adversary should not be able to figure out what the underlying plain text is, or should not be able to figure out any more information about the underlying plain text and what it could have had already. Okay, so this is what we are trying to formally define. Okay, and we will define this using an experiment. So what we will do essentially is we will allow the attacker, themselves to pick two messages. So we are essentially restricting the message space in some sense. So we will allow the attacker to pick two messages in the message space. Okay, so this is either M0 or M1. And what this experiment does is tells the attacker, okay, one of these two messages, we will choose this at random, one of these two messages will be encrypted. So the attacker knows that when it observes a ciphertext C across the channel, it is either the encryption of M0 or the encryption of M1. Okay, and knowing nothing, what is, if the attacker sort of cannot gain any information about the ciphertext C, what would the attacker's guess be for whether that the ciphertext C corresponded to M0 or M1? With what probability would the attacker guess? 50%. Is that what you said? Yeah. And you said you were going to half, right? Exactly, right? So, because, okay, the attacker knows either M0 or M1 is going to get encrypted, it knows one of these two will be selected with probability half. So, essentially when it sees C, it can just guess 0 with probability half or 1 with probability half, and it will succeed with probability half, right? If, of course, the scheme is secure. So, that's really what we are trying to formalize here. So, the adversary outputs a pair of messages M0 and M1. Either M0 or M1 is selected with probability half, and a challenge ciphertext C is computed and given to A. Then A outputs a bit B prime, right? So, B prime indicating whether M0 or M1 was selected. Okay, so if B prime equals B, the output of the experiment is 1, otherwise the output of the experiment is 0. Okay, and essentially what we will try to formalize is this scheme is quote unquote secure if the probability with which an adversary succeeds in this experiment is half as per your guesses. Okay, so this is what the definition would say. So let me write down the formal definition. Okay, I'm running out of space, so maybe I'll just erase this. Right, so an encryption scheme pi consisting of gen, enc and dec with message space M is perfectly indistinguishable for every A, it holds that probability priv k EAV A comma pi is 1 is half. Right? So essentially what we are saying is that consider this experiment, right? So the adversary outputs a pair of messages, one of them is chosen uniformly at random, and the encryption of that message is given to A. Now has C, and after observing C just outputs a bit B prime. So essentially it's guess for which among the two messages was encrypted. And if the adversary can do no better than guessing that it was a 0 or 1 with no better than probability half, then we say the scheme is perfectly indistinguishable, right? So essentially what this implies is that even after observing the ciphertext C, the adversary's knowledge of which was the underlying message that was encrypted is no better than its knowledge as to how one of the two messages was chosen for encryption, right? So that is really what this is saying here, right? So and we call this definition perfectly indistinguishable. Okay, so just to sort of recall, we were talking in order to formalize security, we need to consider what is our notion of security. So now this is our notion of security, right? We were also talking about what is the power of the adversary that we are considering. Again, notice that we are saying that this holds for every adversary A. So we are not really actually placing any computational bounds on the attacker A in this definition. Okay, so it holds for every A, and actually I'll come to this in a bit. Maybe this is too strong and we might need to weaken it to achieve efficient schemes, and I will come to that later. So this holds for every A. And I also talked about, for instance, we discussed informally what chosen plaintext attacks was, and we are now in the eavesdropping setting. So can you see in this experiment how it is captured that we are in this eavesdropping setting that I talked about? Right, so we were discussing that, okay, in this definition that we will look at, we are only allowing the attacker to observe a single ciphertext that is being sent across the channel. It's not observing multiple ciphertexts, it's not getting ciphertext of plaintext that it chooses and then getting to decide what the underlying plaintext is. Yeah?
How can we say that it's not getting ciphertext of plaintext that it chooses?
Yeah, so that's the question. Good question. What is the answer? So we are defining this experiment, and the definition is with respect to this experiment. In this experiment, is the adversary having this power? In this experiment, can the adversary choose messages of its choice and obtain ciphertext? Do you see any provision for that in this experiment? No, right? Yeah, essentially that is not happening because we are defining security with respect to this experiment, right? So in this experiment, this is the behavior of A, right? So we are, whatever we were trying to model informally, right? So we were modeling some sender and receiver and a ciphertext C that is observed by the adversary, right? So essentially that is being modeled by the adversary is only given this ciphertext C. It is not given anything else. There is nothing else for the adversary to observe. There is no other way for the adversary to get ciphertext, okay? Because we are defining the security of the scheme with respect to this experiment, and this is the experiment in which A is participating. Okay, so that is how this is being, the power of the adversary and sort of the ways in which the adversary can act is being captured via this experiment. Does that make sense? So I'll just leave the experiment up for another minute. So can you think about it and tell me?
If the probability goes down to 0, then we cannot find out the encrypted text itself.
Is that true? So essentially, right, so it's perfectly indistinguishable if it is half. So this being half implies that the adversary gets B prime right, so the underlying plain text right with probability half. But if it were to get the underlying plain text right with probability 1, what would that mean?
It's not really distinguishable.
Exactly, and it's not secure, right? So when it is anything other than half, it implies it's not perfectly indistinguishable. And hence the adversary can learn something about the underlying message based on observation of the ciphertext. But yeah, that's a good question, and that was actually the question I was going to ask next. Right, so it is essentially the fact that this is half implies that the adversary can guess the bit B prime only with probability half, implying that, essentially it is not gaining any knowledge after observing the ciphertext C. So if it were anything different from half, it would mean that there is something that has changed about its knowledge of the underlying distribution of MB, right? So whether it was M0 or M1 with probability half. So if this was anything different, it would imply that, okay, after observing the ciphertext C, the adversary is able to guess that it's M0 with probability 1/4 and M1 with probability 1/6 or something, right? Which would imply, based on our discussion, that it's not secure, and that's why it will not be perfectly indistinguishable. And actually, what I want to do next is, in fact, we will sort of work through an example to get familiarized with this definition, because sort of the rest of the day we will be looking at definitions that are of this form. Even if not exactly this definition, they will be in the form of defining an experiment to exactly understand what is the adversarial capability that we are looking at, and then an associated definition that relates to that experiment. Okay. Other questions? Yeah.
And what is the message space built of?
So message space might be defined by the scheme pi, right? So for instance, if it were one-time pad, the message space would be like set of all L bit strings. Okay, so that is defined by the encryption scheme pi that you are considering.
So how does adversary know that?
So the adversary, right, so actually good question. The other thing that I needed to have established, apart from the key K when we talk about security is being kept in secret, is that we are following something called the Kirchhoff's principle. I don't know if you've come across this before or yesterday. So essentially that throughout, the only thing that is being kept secret in these discussions is the key K. Nothing else about the scheme is kept secret. So the adversary will know exactly what pi is, exactly what the key generation algorithm is, exactly what the encryption algorithm is, what the decryption algorithm is, what the message space is. So the adversary knows all of that. The only thing that is kept secret is the key K. Okay, so actually, again, if we are thinking about classical settings, maybe like a few centuries ago, people considered, maybe we sort of, hide the encryption algorithm, right? So then maybe the adversary doesn't even know what to try, and for various reasons, these things have been discarded. You can't really actually do it well. Even like keeping something secret is already hard enough. Something small secret is hard enough. So everything about pi is known to the adversary, only the key K is kept secret, completely secret. Other questions? So, yeah, so then I think what I want to do is to familiarize us with the definition. I would like to work through an example. So actually, Prof. Ashwini, so when are we taking? 11:15, okay. So, right, I mean, because it's important, let me also write this, right? So an encryption scheme, so we saw two definitions so far. One is perfect secrecy, that was a bit more maybe wonky, and this one, right? So an encryption scheme is perfectly secret if and only if it is perfectly indistinguishable. Okay, so the two definitions that we saw are actually equivalent, and this is the definition that we will be working with, because it's sort of easier to compute probabilities in this manner rather than working with conditional probabilities where mistakes could occur. Okay, so now, so I want us to work through this example. Okay, so what we will show, so we considered, we discussed the visionaire cipher, right? and we talked about how it is not perfectly secret in most settings. So let's actually try to show that using this definition that we have seen. Okay. Okay, so we will consider so an example. So consider the Vigenère cipher, okay, with key length either 1 or 2. Chosen uniformly to be either 1 or 2. Okay, and the message space to be the set of 2 character strings. Okay, so essentially, right, the message space is now the set of 2 character strings, so like A, B, whatever, 2 character strings, right? And then the encryption algorithm, essentially the encryption scheme is the Vigenère cipher, and we either, the key is either of length 1 or of length 2, and the key length is chosen uniformly and the keys also are chosen uniformly, as you would imagine. Okay, and now we want to show, so let's consider, right, so this is, the setting is okay. Okay, so we are now only defined the encryption scheme pi. Okay, so now if we want to say compute probability priv k AV A comma phi for a specific adversary A, let's see how we would do that. Okay, so let's consider the following adversary, right? So consider this A. Okay, A. So in order to define A, what are the things that we would need to do? In order to define A, we first have to define the messages, the pair of messages that A would output. Okay. Now after A outputs the pair of messages, a key case are generated, uniform bit B is chosen, ciphertext C corresponding to MB is encrypted and given to A, and A outputs a bit B prime, right. So essentially we have to first define the pair of messages that A would output, and we also have to define how A outputs a bit B prime after observing C. Okay, so that is what we will do. So consider, so this specific A, okay, so this is just an example. This A outputs M0 as AA and M1 as AB. Okay, so do these two messages belong to the message space? Right, because the message space are 2 characters that we are considering are 2 character strings, M0 and M1 are both 2 character strings. Okay, so this A is outputting these messages M0 and M1. So the first step of the experiment is done. In the second step of the experiment, A will obtain a ciphertext C, right. So here A has nothing to do, right. A is just sort of like, silently on the side. This is being done without the involvement of A. A just gets the ciphertext C. But in the third step, A needs to output a bit B prime after observing C, okay. And this specific adversary A does the following, okay. So upon receiving the challenge ciphertext C as C1, C2, it does the following. If C1 equals C2, output 0, otherwise output 1. Okay. So this is the example adversary that we are considering. Okay, so this adversary outputs these 2 messages M0 and M1, receives a challenge ciphertext C, say we pass a silent ciphertext C that will consist of 2 characters as C1, C2. It checks if the 2 characters are equal. If so, it outputs 0. So when I say output 0, what does that mean? I am saying that B prime is 0, right? Otherwise, it outputs 1, in which case if C1 and C2 are not equal, A's B prime is 1. So when they are equal, A is guessing that M0 was encrypted, and when they are not equal, A is guessing that M1 was encrypted. Okay, so this is the adversary. Now the experiment is well defined, and one can ask, so compute probability priv k EAV A comma pi is 1 for this adversary A. Okay, so pi is this pi, the visionaire cipher with message space consisting of 2 character strings and the key length either 1 or 2 chosen uniformly, right? And this is the adversary A. And essentially, when we want to compute this probability, we are essentially computing the probability that B prime equals B. Okay, so that is what we want to do. Okay, and we will do this so that we get familiarized with the definition. So before we take a step forward, I just want you to think about how you would do it. And think about if the question is making sense. So is the question making sense at least? Forget the answer for now. Question is okay? Yeah? This one? This one. Oh, why is it choosing this strategy? So, this is how we have defined this adversary. You can consider another adversary that does something else. That's completely fine. But this is just how we are defining this adversary. Okay, and of course, if this strategy doesn't let it sort of succeed in the experiment, maybe A will do something else. Okay, but this is just how we are defining the adversary, and maybe if your question is how do we even come up with strategies, that we can talk about a bit later. Okay, so maybe depending on sort of the scheme, you will try out various things, but for now let's just say that this is the adversary that we are considering. Okay. So essentially for this adversary, we want to compute this probability. Okay, so to start off with, right, we could yeah.
We're supposed to be using a key over there, right, for computing that.
Yeah.
And we can just choose any arbitrary.
No, so the key K is generated by using the key generation algorithm here.
Yeah, but over here in this particular experiment,
Yeah.
our generation algorithm is what is it?
So, right, so essentially the A is participating in this experiment. Okay, so what A does is only the steps that A needs to do. So, A outputs a pair of messages M0, M1. Okay, and the second part of the experiment, see, depending on how it is defined, for instance, in some other textbooks or some other ways to define it, one would view this as sort of an interaction between an adversary and a challenger. So, the challenger is the one generating the key K and so on and so forth. So, I am not taking that view necessarily, but really A is taking part in that experiment. Somehow a key K is generated by the key using the key generation algorithm. So, this is sort of something that A is not involved in. So, A is sending, you can think of this in the following way, right. So, there is an adversary A that sends M0, M1 to the void, right, and here a key K is generated using the key generation algorithm, a bit B is chosen uniformly from 0, 1, and then C is computed as the encryption of MB, where MB is either M0 or M1 depending on B, and this is sent to, the C is sent to A, and now A outputs B prime.
Yes, ma'am. My question is that void over there.
Yeah.
As the person who overseeing this experiment sort of.
Yeah.
Do we also do the computations for the void, or do we consider the void?
When you say we, you mean the adversary?
We as in the observer who is observing the experiment.
So if you want, if it makes it easier for you, you can think of this as some challenger who's doing all of this or whatever, some person, and we are not involved.
Because the idea is that the probability is computed and there has to be somebody who is computing that probability.
I mean, so yeah, so essentially, right, the probability, okay, as in you can think of as the challenger computing the probability if you want, it doesn't matter. But essentially, right, really sort of the thing to focus on is that the adversary's role is only this. It outputs M0, M1, receives C, and then outputs B prime, right? So, essentially when you compute this probability, it can be whoever that is computing the probability. So, that is maybe not of relevance here. What is of relevance is that the key K is generated by using the key generation algorithm and is not known to A. Okay, so that's all.
Like, how is C created then? Like for
C is
do we
created.
have an abstract definition for C, like in
So C is created as the encryption of MB under key K. So if you want, think of there being another party who's, so we'll call the party challenger, who is doing all of this. Okay, and you can even think that the challenger is computing the probability. So A itself could possibly compute the probability as well, but that's regardless. But yeah, if it helps, you can think that A is interacting with somebody on the other side in this experiment, and that other person is computing the key K, is transferring the ciphertext C to A, and A only engages in this part, and it's meaningful to then ask what this is when A is well defined. Okay. So maybe, maybe we'll pick this up after the break. You can even try to think about it. So just to sort of give you a hint, right, I'll just take one more minute to compute this probability, right. So you can just compute the probability that A succeeds or this experiment is 1 when B is 0 times probability B is 0 plus probability that A succeeds when B is 1 times probability B is 1. So then when you think of it this way, when you fix the B, you know exactly which among the two messages are getting encrypted, and maybe computing the probability is a bit more easier, right? So you can split it in these two steps and try to compute, but we can talk about it a bit more after the break. Any other last questions just on the setting? Yeah. So key length is either 1 or 2, and it's either 1 or 2 with uniform probability. No, it doesn't know. This is all, so this is how the scheme is defined. So the key generation is essentially, the key generation algorithm for the scheme says choose either 1 or 2 with probability half. Once that key is chosen, choose a key from the appropriate key space. Okay, so any other questions? Okay, let's stop here then for